Okay, so this is a quick video about Compton scattering. Compton scattering is really a theory about collisions. It's a collision between an incoming photon and a stationary electron. You may say, what do you mean stationary electron? What electron is just sitting around waiting to be hit? They're all moving everywhere all the time. Sure, but we can always attack the problem in the rest frame of the electron. In other words, let's pretend that we're sitting on the electron. We'll see what the problem looks like in that frame because it's easier to solve. And then if you're interested in what it looks like somewhere else, okay, fine, switch frames. It's not a big deal. But the algebra is a lot cleaner in this one. Another thing that's interesting about Compton scattering is you always see it in the same section as photoelectric effect. And that is because in order to get a correct analysis in Compton scattering, you basically treat the photon as if it's a ball. And this is one ball crashing into another ball. And we know what happens when two balls crash into each other. They go careening off in whatever directions they go off at. At first, the electron was at rest, but now it's not at rest because it's been crashed into. The photon leaves at one angle, the electron leaves at another. The electron has some kinetic energy now. The outgoing photon presumably has less energy than the incoming photon because the incoming photon has split its energy between these two things. Now, notice I've also drawn the outgoing photon a different color. I didn't do that only to make the diagram pretty. I did it because when this happens, the incoming photon will be a different color than the outgoing photon. Why is that? That is because, if you recall, the energy of a photon is given by this, and the momentum of a photon is given by this. This is all of this de Broglie wavelength stuff. So light has particle properties and wave properties. The wavelength defines the wave properties, and then it has these particle properties. So it has momentum. So as the wavelength becomes a different number, you'll have a different energy coming in, and you have a different energy coming out because some of the energy goes to the electron. So if you have a different outgoing energy, then you have to have a different color. A different wavelength means a different color. Okay, so all this problem is a collision, and we know how to do collision problems. Collision problems are conservation of energy and conservation of momentum. What this says is that the kinetic energy left over for the electron is however much energy you start with minus however much energy you spend on the outgoing photon. Whatever's left, the electron gets that. The other thing that's true is conservation of momentum. We have a certain amount of momentum on our incoming photon and a certain amount of momentum on the outgoing photon. Whatever's left over goes to the electron. It's a little trickier than that, though, because momentum is a vector, and it's not true that magnitude of momentum is conserved. It is true that vector momentum is conserved. And so there's a little tiny extra step we have to take, which is break into components. And so we can say, okay, fine, the x component of the electron's momentum is this, and the y component of the electron's momentum is that. This is because we've set this up in such a way so that the incoming momentum is purely in the x direction. So whatever the momenta of these two particles are, they'd better add up to give something that looks like this, is only in the x direction. So this just says that their y components have to be opposite each other. Don't let the minus sign bother you too much. It just means that if one points up, the other one points down. They have to in order to cancel, right? And then this just says whatever momentum the incoming photon had, it was all in the x. Whatever x momentum it gives to the outgoing photon, whatever's left over goes to the electron. Kind of just like the energy at that point. Okay, there's only one more piece we need for all this, and this is the formula that everyone wants to see. This is the Compton scattering formula, and it tells you something about the wavelength of the outgoing photon, lambda prime, versus the wavelength of the incoming photon, lambda. Okay, this guy here, this h over mec, it's just a number. H is a fundamental constant, the mass of the electron is a constant, c is the speed of light. So often you'll see this written like this. And this gives you a sense of how big this scale is. Look, on this side, this is the change in wavelength. How much does the color change by? It changes by around this amount. This 1 minus cosine theta, it can go anywhere from 0 to 2. And so, okay, the biggest shift you could possibly have is about twice this. But that is small, man. The wavelength of light, like green light, for example, is 500 nanometers, and here we're talking about 2.43. It's like 100,000 times smaller. It's super small. And so this is an effect that is small, and you don't see it with visible light. That's why when you always see Compton scattering experiments, they give such small wavelengths, and they always talk about X-rays, because you can see the difference much easier with an X-ray than you can with visible light. Okay, the other thing that's worth mentioning is this is not an independent formula that can't be derived from elsewhere. And you also don't need quantum field theory to derive it either. I said that this is a collision, and if you use special relativity together with conservation of momentum and conservation of energy, you can derive the Compton wavelength formula. There's a bunch of videos online that do that. I'll include it here just for completeness. I'm not going to go through this algebra soup with you because it isn't particularly pleasant, but I'll just show, look, conservation of momentum, conservation of energy, algebra, 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 algebra. At the very end, you plug in the de Broglie wavelength and boom, you're done. You can pause the video if you want to double check my algebra and make sure I didn't cheat. But that's the idea. I include it just to really stress the point that these are ideas from the first introductory physics course you took. They're just the rules of mechanics together with this weird de Broglie wavelength stuff and, okay, a little bit of special relativity too. Okay, so what's next? If I take these two formulas and I basically plug in all these other things that I've set up in the problem, I end up with these four relationships. These are what we're going to use to solve every single Compton scattering problem we have. You might say, oh, 4 equations. Oh, that seems like a lot. Look at all those primes. Look at all those cosines. Honestly, I'll take you through an example problem. It's really not that bad now that we've laid it out. The hard part is getting the Compton scattering formula. Once you have it, you just park all this stuff up here and let me give you an example of a problem and basically how you can just grind it out at this point. So here we have an example. A photon has some very small wavelength. This is an X-ray, by the way. Remember, I always said you don't see much effect from this unless you use a small one. Okay, and they give you a scattering angle. And from that information alone, they want you to find phi. That's crazy. I didn't talk about phi at all when I was doing my derivations, right? So how could I possibly be expected to find phi? Okay, so this is what I say. If you don't know how to calculate what they're asking for, you calculate what you do know how to calculate. They give us the angle. They give us the initial wavelength. Let's find the new wavelength. Lambda prime. Lambda prime is the original wavelength plus this extra bit that we get. And if you do that, we go from 2 to 2.25 times 10 to the minus 12. Again, small effect. It's a small effect. Okay, well, now that I have the wavelength, maybe, I don't know, let's calculate the momentum, because I can certainly do that. I have the angle, I have the new wavelength. I can do that. Boom, plug and chug. I get a couple of numbers. Okay, now what are they interested in? They're interested in phi, this angle. But if you think about it, whatever angle this is moving at, well, that's like its momentum in the y direction, and this is its momentum in the x direction. So tan phi, not so bad. Tan phi is PEY over PEX. That is a division, and you can easily solve for the angle, which is 62.85 degrees. Okay, but what if the problem asks for, I don't know, how fast is the electron going? Okay, well, let's look at it this way. Let's find the velocity of the electron, and let's assume it's non-relativistic and see what we get. I know what you're saying. You're like, wait a minute, didn't you use special relativity to get the Compton formula? Yeah, I did. But if it's moving slowly, maybe I can get a close enough answer so that I don't have to deal with special relativity. Those equations are uglier and I'd rather not use them. So let's just see what happens. P is mv, plain old mv. What's the magnitude of P? It's px squared plus pey squared. If I go through and I crunch the numbers, I get 1.59 times 10 to the 8th meters per second, about half the speed of light. So I see this and I say half the speed of light. That doesn't seem okay. We're not 99% the speed of light. That's when relativity starts to dominate, but we're also not going 100 meters a second either. I mean, this is pretty fast. So, okay, let's see how big a difference it made. Okay, so the momentum becomes a little bit more complicated. You got to divide by that gamma factor. But you end up with something that is a little bit different. It's not crazy different. It's maybe, I don't know, 10, 12% off, something like that. But the point is, it's also not drastically different either. You're kind of in the right ballpark. And this is kind of an indication of, I don't know, whether or not you're comfortable with this difference is an indication of whether or not that's a good approximation to make. But often the problem will tell you whether or not you should be relativistic or non-relativistic. Okay, hopefully this helps more than confuses.